Okay. Good afternoon, and thank you for participating at this workshop. I am Giacomo Leone. I am a data scientist at Sorintech. And today I will talk to you about prognostics and health management. So let's start the presentation. Before, I want to show you this chat link. So if you have any question for me, please go to this link and you can write any question during the presentation. We answer you at the end. If you want, you can pause the video, copy the link, and then play again. So let's start. First of all, what is prognostics and health management? So prognostics health management is an engineering discipline that aims to two main objectives. The first is the health assessment of a system under its actual operating condition. And the second is the prediction of its future state in order to provide an effective maintenance strategy. So we can say that PHM has two main outputs: a diagnostic output in order to provide information about the health state of the system, and a prognostic output in order to provide an estimation of the remaining useful life, the so-called rule, of the system under analysis. That is how much the system will work. Both the outputs go in the direction of the optimization of the maintenance strategies. Indeed, prognostic health management is strictly related to the concept of condition-based maintenance. Condition-based maintenance is a management philosophy for which the decision to repair or replace a system is based on its current or future condition, so that the actual maintenance intervention is performed only when an impending failure is detected. So not too much early in order to exploit the system at the maximum, but of course not too late in order to avoid the failure. So which are the benefits then of performing PHM and condition-based maintenance? They are summarized in this picture, and they are optimization of the maintenance scheduling, which leads to a reduction of time to acquire, to buy spare parts, hence achievement of near zero downtime, and finally, significant cost savings. But what do we need in order to perform prognostic health management? Of course, we need data about the failure. So which are the failures which occur to the system, which are the causes, and which are the signals correlated to the failure. So we have two options. If we can monitor the condition of the system through a condition monitoring system, sensors, then we can develop algorithms which are based on such data. And then we can develop different kind of models, which are usually of three classes: physics-based models, data-driven models, and hybrid models, which are a mix of the two previous classes. On the other hand, if we cannot monitor the system, we have to develop algorithms which rely on other sources, such as failure reports, literature investigation, or experts' belief. Today, we will focus about data-driven models. So, first of all, what are data-driven models? They are models which are based on the analysis of data about a specific system. And the goal is to find the relationships between the monitoring signals, for instance, vibration, temperature, power absorption, and the degradation process. The main advantage of data-driven models is that no explicit knowledge of the physical behavior of the system is required. And this is a great advantage, especially when dealing with the complex system, for which the definition of a physical model is quite complicated. Finally, data-driven models provide a good trade-off between model complexity and results accuracy. Also, another motivation for developing data-driven models is given by the current industrial scenario, which is based on modern concepts of Industry 4.0, Internet of Things, big data, which enable the increase of the data availability coming from condition monitoring systems. So today, in order to show you an example of prognostic application, we will see a practical case study, which is based on the analysis of a dataset about degradation simulations of turbofan engines. Such a dataset is provided by NASA, which made some simulation about the degradation of turbofan engines. In particular, more in detail, they simulated 21 sensors, which are used to characterize the fault evolution of the engines. And the signals the analyzed signals are of heterogeneous nature. So they monitored the temperature, pressure, fuel flow, fan speed, etc. And they recorded signals of engines working at different operational conditions and they experience different failure modes. A failure mode is how a system fails. For instance, if we think about a motor and an engine, it can fail, for instance, due to overheating, or for instance, due to mechanical problems. So different failure modes correspond, of course, to different trend of the signals. For instance, when an engine fails because of overheating, it is likely to find a trend, an increase in the monitor temperature. On the other hand, if the motor fails due to mechanical problems, for instance, we can expect a trend, a drift in the monitored vibrations. The dataset is composed in this way. There is a training set, which is composed by run-to-failure degradation data of 100 engines. It means that 100 engines are monitored, and we collect data for each of them until it fails. So we have the complete history. On the other hand, we have a test set composed by, again, 100 engines, for which we have partial degradation data. That is, such engines are not failed yet. And the objective of our analysis is to forecast the remaining useful life of such engines. Since we have the data of 100 engines which are already failed, so we know the degradation process of such engines, I propose for our analysis a similarity-based prognostic approach. Such algorithms represent an interesting class of data-driven prognostic approaches, and they rely on run-to-failure historical data of multiple units, historical data of multiple units, like our test set, which I just described. Then the rule forecast for a given engine, for a given item, for which the rule has to be predicted, is performed through a similarity assessment between the degradation pattern of such test item with the training patterns, so with the degradation pattern of the items already failed. I will show you now how to perform such analysis in our example. So first of all, we have to analyze the training patterns. Why so? Because for each engine, we have the records about 21 signals. So the first questions one should ask is, how can we combine such signals in order to extract information about the engine degradation? And then, are all of such 21 signals useful in order to predict failure time? So let's answer to the last question in order to make a signal selection. So let us suppose that, of course, degradation is a process which increases over time. And as long as degradation increases, it is reasonable to expect that there will be changes in the value of those signals correlated to the degradation. So in the example of before, if there is an overheating failure, we have to expect a change in the temperature. So it is also reasonable to expect a monotonic trend of the signals correlated to the degradation. So such signals should increase or decrease over time. So what we do is to compute a monotonicity index for each of the 21 signals. So such index is computed as shown in the formula. What we do is to take the delta of the signal over time, where the delta is the difference of the signal at 2 consecutive timestamps, and then count how many positive deltas there are and how many negative deltas, and then compute the difference, the absolute difference between such numbers. So if a signal is quite constant over time, we expect that the number of positive and negative deltas is quite the same, so that monotonicity will tend to 0. Instead, if a signal, for instance, tends to increase over time, we will have much more positive deltas, and so monotonicity will tend to 1. So what we do is to compute the monotonicity of each signals, and we select only those signals with higher values of monotonicity, and discard the ones with lower monotonicity, as shown in the picture. In this picture, we see that the signal coming from sensor 14 on the left is quite constant, so its monotonicity is low, and such signal will be discarded. On the other hand, the signal coming from sensor 12 is monotonic, tends to decrease, and it will be selected. Through this process, the result is that we have selected 7 signals out of the initial 21. So we did a great selection, a good job about signal selection. But the next question is how to correlate such 7 signals with degradation. How can we extract information about the ongoing degradation? So in order to answer to this, let me introduce the principal component analysis, the PCA. The PCA is a method very useful to extract relevant information from confusing data sets, which appear, for instance, unclear and redundant. And this is our case, because we have a data set now with 7 signals. We know that such signals are monotonic over time, but we have to extract the information about degradation from such signals. PCA, in particular, technically speaking, is a mathematical method that converts a set of observations of correlated variables, like our 7 signals, into a set of uncorrelated variables called principal components. So what PCA does is a space transformation. We start from a set of signals of variables correlated and transform the signals into another set of variables which are uncorrelated. But both the sets of variables have the same information content. So this is very important. They have the same information content. Another reason the reason for which we do such transformation is that PCA is defined in such a way that the number of principal components, so the component, the variables of the transformed space, is less or equal than the number of original variables. So we started with 7 signals, and we will end up with a lower number of signals. So again, we do a space reduction, signal selection. Furthermore, the transformation is defined in such a way that the first principal component, so the first variable of the new space, accounts for most of the variability in the data. That is, it retains most of the information. Then there is the second component that has less information, and the third less, and so on. So we can extract few variables, few principal components, which has all the relevant information of the starting dataset. So how can we use PCA in our example? First of all, what we can do is to have a representation of the status of each engine in the training patterns when the engine is approaching the failure. So in order to do so, for each engine, we select the last 10 records of each variable, of each of the 7 variables, and compute its mean. Finally, doing so for each of the training engines, we ended up with a matrix composed by 100 rows, each for each training engine, and 7 columns, each for a column for each signal. Then, applying the PCA, we ended up in a situation like the one described in the picture. So, through the PCA, we started from 7 signals, and we ended up with just 2 signals, the first and the second principal component. And you can see also that through the PCA, we split the data in 2 clusters. Here, each in the picture, each point represents the failure state, the final state of the engine, of an engine. So each point is an engine. And the PCA worked in such a way that separated the engines in 2 regions, one for each failure mode. As I said before, in the dataset, there are a simulation of different operating condition at different failure modes. And so, as I said, at different failure modes correspond different trend of the signals. And through the PCA, without making any assumption on such trends, we managed to find different clusters, so the motors which failed for different failure modes. Also, we can see that the first cluster in blue is characterized by the fact that PC1, the first principal component on the horizontal axis, has a value around -4. So that we can assume that when an engine will fail according to failure mode 1, his principal component 1 will have a value around 4. For failure mode 2, the final value of PCA 1 will be 4, +4. So that picture was related to the final values of the time series of each engine. But if we apply the PCA to the complete time series of each engine, we will obtain a picture like the one depicted in this slide. So we have the complete time series of the 7 signal of each engine. We apply PCA, and we plot the trend of the first principal component over time. So in this picture, each curve, each line is the trend of PC1, first principal component, for each engine. We can see that the principal component 1 is monotonic over time. Not only, there is a different trend for each cluster. So for failure mode 1, the value of principal component 1 will tend to decrease. For failure mode 2, the principal component will tend to increase. And also, since the principal component 1 is monotonic over time, we can use it as proxy, as equivalent signal for the degradation. So it is the principal component 1 which will inform us about the degradation. So thanks to PCA and monotonicity index, we started from 7 signals and ended up with just one uniform signal, the principal component 1, that inform us about the degradation. What can do in this stage is to fit the trend of the principal component 1 of each training engine over time. So we fit such a trend by means of an exponential degradation model, and the formula is shown in the slide. Why this model? Because it is very flexible model, so it allows to fit different shape of monotonic trends, and also it is very easy to fit because of the few parameters involved. So now that we analyzed the training patterns, the obvious question is how we can exploit such information in order to predict the remaining useful life for a not failed engine, which is the main objective of prognostics. So the similarity algorithm, which I propose, is composed as follows. So the first step is to pre-process the test pattern. So in this pre-processing, we do the same things that I showed previously for the training pattern. So we extract the 7 monotonic signal and then apply PCA, so that we have a partial information about the degradation, which is the trend of the principal component 1 up to the observed time. Then the second step is to compute the distance between the degradation patterns. But which distance? So we compute the distance between the degradation pattern of the test item, that is the item for which we want to forecast the rule, and each training pattern. So we compute the Euclidean distance between such patterns. Why we do so? Because the hypothesis is that the smaller is the distance, the more similar are the degradation process of the two products. That is, if two products have similar degradation process, their degradation pattern will be very similar, so there will be small distance. The third step is to assign a similarity score to each training pattern. So the similarity score is computed as the inverse of the distance. Again, because small distance means higher similarity. So higher score, W. We call the score W. The final step is to make the rule forecast. So first of all, let us denote as H star the last value known for the degradation of the test item. So we know the degradation for our engine for which we want to forecast the rule up to a value H star. What we do is to take for each training pattern, for the generic training pattern I, to calculate the remaining useful life of the training engine I, when its degradation pattern was equal to H star. So we see how many cycles it worked after its degradation pattern was equal to H star. Why we do so? So we do so because if the two patterns are very similar, then it will be very likely that our test engine will have the same remaining useful life. How much it will be probably likely such event? Well, the probability that given a training engine I, the probability Pi that the test rule will have, the test engine will have the same remaining useful life of engine I, it will be obtained by normalizing the similarity score. That is, we take the sum of the similarity score of each of the 100 training engines, we sum, and then we take the training score of each engine and divide it by such sum. Of course, with this formula, it is obvious that the higher is the similarity score of an engine, the higher will be the associated probability. So at this point, in the end, we will have m, for our test engine, m possible values for the final rule, where m is the number of training patterns. In our example, 100. So each value of rule will have a given probability. So we can exploit this information in order to obtain a probability distribution for the final rule. And we can exploit the probability distribution in order to provide a confidence interval, which will express our uncertainty about rule forecast. Because, of course, in such applications, in my opinion, it does make sense to give a point estimate about the rule. So, because we cannot be 100% sure, for instance, that an engine will fail into 20 cycles, because we cannot be sure. But instead, it's much more useful to give a confidence interval. Let's say, for instance, that the engine will fail between 18 and 22 cycles, because in this way, the information we provide is much more useful for maintenance, scheduling, and operation. Another output of our algorithm is that it is possible to forecast for which failure mode the test item will fail. Indeed, for instance, the probability that failure mode, the engine will fail with failure mode 1 will be equal to the sum of the probability associated to all the training patterns which belongs to the cluster 1. So these are the results for one test item. So in the picture on the left, we see that the orange curves are the degradation of the training engines which failed according to failure mode 2. Instead, in blue, there are the curves of the engines which failed according to failure mode 1. In black, there is the partial degradation observed for the test engine. And with the black crosses, there are which are the closest curve, the closest degradation pattern to our test pattern. So in this way, we can select the closest curve, so the ones with higher similarity score, and as I shown before, we can extract a probability distribution for the remaining useful life of our test engine. So I'm referring to the picture on the right. In the picture on the right, on the horizontal axis, we can see with the red dot the mean value of our forecast, and with a green cross, the actual remaining useful life. And we can see that our prediction, the mean value, is very close to the actual rule of the engines. Not only, we can provide also a confidence interval. In the picture is shown by the purple markers. In this case, the algorithm output was that the remaining useful life of the engine was between 20 and 29. Also, the algorithm outputted the probability that the failure of the failure mode which will occur. In this case, the algorithm was sure that the failure mode would be failure mode 2, because the probability of such failure mode is equal to 1. And of course, the picture on the left justifies this output, because we can see that the degradation of the test item is much closer to the degradation of the engines which failed according to failure mode 2. Okay, so the algorithm has been run for each of 100 test items, the test engines items were at different stage of life. So some of them were very close to failure, and others were at the early stage of life. And in the 87% of the cases, the actual rule value have fallen into the forecasted confidence interval. Also, the forecast error, computed as the absolute difference between the mean rule forecast and the actual rule, decreases when approaching the failure. So in the picture here, we can see that, for instance, the first point, when the actual rule of the engine was between 0 and 20, the mean difference, the mean difference error of the algorithm was about just 2 cycles of error. And the error, of course, increases when the actual rule is larger. For instance, of course, this is justified by the fact that, for instance, if the engine have a rule of 140 cycles, so it means that it is at the early stage of life. So we have still a few data about its degradation, and so an error, forecast error, will be more likely. Also, as the engine approaches the failure, so its actual rule decreases. Of course, also the rule forecast uncertainty of the model decreases because we have more information. So the uncertainty of the output will be lower. That is, the confidence interval width will be lower. And this also is very useful for scheduling maintenance operations. So, in conclusion, I show a practical example of prognostic application. In particular, a mix of techniques for feature extraction, reduction, and fusion, and also curve fitting have been presented. I want to emphasize that no expertise about two-profile engines was necessary. Of course, it is beneficial, but it's not necessary if we have enough data. In our cases, in our test set, the data-driven prognostic model has resulted as an effective tool. In particular, there were good performances because 87% of the prediction were good, correct, and the forecast error has decreased when the actual rule was lower, so when the engines were approaching the failure, and also the output uncertainty has decreased when the engine was close to failure. Also, another possible output of the algorithm is to forecast not only the remaining useful life, but also about which failure mode will occur. So, thank you for your information. This is my email. If you want to ask me, have any comment or opinion about my presentation, and I wait for you in the one-to-one session for further questions. Thank you.